Good morning, Porters, or good afternoon. At any rate, my name is Mr. King, and I'm going to talk to you about Lewis structures today. Today is just an introduction. So I'm going to talk about atoms, ions, and ionic compounds. We'll cover covalent compounds later. All right. So Lewis structures are named after an American chemist named Gilbert Lewis. In the 1920s, he developed a way to keep track of valence electrons, which is an important thing because when you think about it, when two atoms bond with each other, it's the valence electrons that are usually the things that are doing the interacting, which means knowing how many valence electrons there are helps us to predict how the hell they react. Lewis actually got a Nobel Prize for this methodology, and it's something that we still use today, which is probably why he got a Nobel Prize. It's something that lasts. Basic idea is this. When you want to draw what's called a Lewis diagram, if you're trying to do a single atom, you use the chemical symbol to represent the nucleus of the atom as well as all the core electrons. And you only show the valence electrons around that. There's 4 sides to a chemical symbol, so you use a dot on each side of that symbol to represent how many valence electrons there are. Carbon is my favorite element to talk about. Oops, don't have the pen. It is active. There we go. So carbon is my favorite to talk about because it's the element that makes all life here on Earth, right? And carbon has 4 valence electrons. That is one of the reasons why it is so integral to life, is because it can bond so many different ways. But because there's 4 sides, we wind up representing 1 electron on each of the 4 sides. That's basically the Lewis structure for carbon. Let me show you a couple other Lewis structures, right? Hydrogen, found in group 1, can be represented this way. Beryllium, found in group 2, can be represented this way. Oh, let's see. Let me erase that and try again. So beryllium can be represented in this way. We got the 2 electrons. Notice we don't really pair up the electrons until we have enough. And that's one of the things that Lewis has in his model. Fluorine is found way the heck over here, has 7 valence electrons. So I've drawn 4, and now that I've drawn 4, I'll start pairing up. And fluorine looks like that. Oxygen winds up looking a little bit like this. Oxygen has 6 valence electrons. So it looks like that. Okay. Now, some people at this point will say, hey, could I draw hydrogen this way? Or like this? Or could I even put the dot on the bottom? Because sometimes we want things to look the same, we teach things as starting at the 12 o'clock station and moving your way around clockwise, putting a single electron in. Although there's completely nothing wrong with drawing the dots in a different location if that helps. You'll see later on that that might help later on. Okay, but that won't be till we get to covalent compounds. All right. Why don't you take a moment, pause the video, and practice these 4 atoms. All right, so now that you've practiced these 4 atoms, let me go over this real quick. Nitrogen is here on the periodic table. It has an electron configuration of 2s2, 2p3, which means it's got 5 valence electrons. So I'm going to go ahead and draw nitrogen and then draw 5 valence electrons so that nitrogen looks like this. Notice it can bond 3 times if we're talking about covalent compounds. Fluorine, oh, we did that one already on the last slide. Hopefully that didn't throw you guys. 1, 2, 3, 4, 5, 6, 7. Neon, there's an explanation here of why neon doesn't like to bond. Neon has 8 valence electrons. Check out its Lewis structure. You can tell by looking at its Lewis structure that it's completely full, and it's not going to want to bond anymore. And silicon is a heck of a lot like carbon. It's right underneath it on the periodic table. It has 4 valence electrons, so it should look like this. All right, time to make it a little harder. We can draw Lewis structures for ions as well, and I don't think that this is really making things that much harder. We have to think a little bit. Like, for instance, we've got hydrogen here with a positive charge. What that means is that normally hydrogen has 1 electron. This hydrogen has a positive charge, so it means it lost an electron. So I am just going to draw it as an H. To indicate that it's an ion, we usually draw in square brackets. And we usually also add the charge outside the square bracket. That way it's pretty obvious about what's going on. So beryllium is going to be drawn in a similar fashion. Beryllium, I'm going to draw the core of it, the nucleus and the core electrons, as Be. And I'll note beryllium usually has 2 valence electrons. But this says that I've lost 2 electrons. So beryllium's Lewis structure is going to wind up looking like this. Again, I put the symbol inside a square bracket to indicate that there's a 2+ charge. Now you might be thinking, wow, this is so much easier. I don't have to draw any dots now. That's only half right. When we get to fluorine, fluorine's an anion, which means that it gains an electron. Normally fluorine has 7 valence electrons, but this charge means that it's got 1 more. So I have to draw a total of 8 for fluorine. Notice I just talked about that it normally has 7. So we draw the first 7 as normal. 1, 2, 3, 4, 5, 6, 7. And then the extra one we usually draw as an X. Again, we put the charge on the outside to indicate that this is a charged ion. And finally, oxygen here. I'm going to put the O in the center. There's usually 6 valence electrons on oxygen. But now I have to show that there are 2 extra electrons. Again, I'm going to use X's to represent the extra electrons. And that's going to be a 2- charge as well. Take a moment and see if you can draw these 3 ions. All right, now that we're back, check this out. Nitrogen is going to look like this. Nitrogen usually has 5 valence electrons according to its placement on the periodic table. So it usually looks like this, but it's got 3 extras. So I'm going to draw 3 X's. And then I'm going to go ahead and put a square bracket and the charge. Fluorine has 7 valence electrons plus the extra 1. So again, that's going to go inside a square bracket with a charge on the outside. And aluminum, well, this one's the easy one because aluminum normally has 3 valence electrons, but the 3+ means that I've lost them. So I'm just going to draw aluminum like that. Now, there's only one more thing to make this harder today. Here's the level of complexity. We want to draw an ionic compound. In table salt, sorry, this is not table salt. In sodium fluoride here, we know that the sodium is going to gain a +1 charge, and the fluorine is going to gain a 1- charge. That's because the sodium is going to lose an electron, and the place the electron winds up going is to fluorine here. So I'm going to draw this as a story and show you how we get the final result. Okay, so sodium normally would look like this, and fluorine normally would look like this. Okay, if I'm trying to make NaF, what's going to wind up happening here in my story, let me change the color real quick, is that this sodium is going to lose an electron, and the fluorine is going to wind up gaining the electron. So ultimately what I wind up with is I wind up with a sodium ion, and then I wind up with a fluorine ion as well. And that fluorine ion is going to have its 7 native electrons, plus it's going to have the 1 extra electron. We draw that 1 extra electron as an X again. Notice This time I decided to draw the X on top, even though I drew it over here on the bottom. It doesn't matter where that extra electron winds up, as long as we see that there's one extra electron, indicating why fluorine's got that charge. Something to talk about conceptually. This sodium fluoride, the reason why it's being kept together is because we have a positive charge and a negative charge. The Coulombic attraction between these two particles is pretty strong, and it holds the two ions close to each other. They can't get far apart from each other because of that Coulombic charge, that force of attraction. All right, for barium chloride, I've got to kind of think this one through. Barium's going to be a 2+ charge, but I've got two of these 1- charges. When I draw my picture, I really don't like my negative charges to be together for the same reason I was talking about up here. The charges are going to attract each other if they're opposite. If they're the same, they're going to repel each other. So when I try and draw my barium chloride, I am going to put my barium in the middle with its 2+ charge. And I'm going to put a chlorine on one side with a 1- charge. And I'm going to put the other chlorine on the other side over here with a 1- charge. This way, I can keep the two negative charges as far apart from each other as possible. They're 180 degrees away from each other. If I had put it over here, they would only be 90 degrees away from each other. And if I had put the other chlorine over here so that it was BaClCl, that's two negative charges together. That would not exist. Okay. Finally, I've got K3N, and I'm gonna think about this one in a pretty similar manner. My potassium is 1 positive, my nitrogen is 3 negative. So I'm gonna put my nitrogen in the middle of this. And it gains 3 extra electrons. That's what the 3 negative means. Potassium lost its electrons, and it goes like that. So potassium doesn't have any extra electrons in here, but nitrogen does. One thing that I'll note is that I like to draw my my cations on the same side as where the extra electrons are. So I don't usually draw my potassium on top because that's where a native pair of electrons is versus the extra electron in nitrogen. I don't think it matters that much, though. It's just me being a little obsessive. All right. If you take a moment, pause, draw these two. All right, now that you're back, magnesium sulfide, magnesium's a 2+ and sulfur is a 2-. That means I can put them side by side because there's only 2 of them. I'm drawing my 2- in the wrong spot. Let me erase that and try it again. 2- goes here, and we wind up having 6 native electrons and 2 non-native electrons. For calcium fluoride, calcium winds up being my 2+ charge. Fluorine winds up being my 1-. I'm going to put my calcium in the middle, and I'm going to put a fluorine on each side. And that's what that's going to look like. Again, the Coulombic attraction is going to be between the positive and the negative, and the positive and the negative, which is why I don't have my 2 negatives next to each other. All right, next lesson, we're going to be talking about covalent bonds and how atoms and molecules share electrons, so the pictures look a little bit different.